2014. It's great to see you all back here again. Hope you had a great evening last night. Sounds like it. Sorry I couldn't join you, but sounds like it was a lot of fun. Also, another welcome to the folks that have joined us on the live stream. We have, last time I just looked about a minute ago, we had over 100 people and a lot of people joining for this morning. So, maybe I should ask you to give a good wave to your community friends out on the internet, but I don't know where the camera is. So. All right, well, wherever you are, guys, hi. All right, oh, it's over there. Okay, so you know the expression the expression about bringing a knife to a gunfight. I realize I'm the guy who is wearing a Hacklang t-shirt at a D-Lang conference, so I apologize for that. It was an inadvertent choice of clothing this morning. But talking of language impedance mismatches, I have a great honor this morning to introduce, I'm not going to say Mr. C++, but almost, one of C++'s greatest advocates, and a man who needs no more introduction from me at least, Scott Meyers. Welcome.
Thank you very much. I don't think I need it. Well, good morning. Andre asked me a few months ago if I would give a talk here, and I said, well, I'd be happy to do that, but I don't really know D. I would think that'd be a problem. He goes, no, really, it's not going to be an issue at all. And I thought, that is one open-minded user community. That's impressive. I said, this is going to be a complete piece of cake. I'm very excited about this. So I put together my talk, the last thing D needs. Sitting down, I was feeling comfortable, things were going great, and then I got a missive from Walter. Walter, the Bjarna of D. He said, having a relevant picture in your presentation can make it more interesting and visually appealing. Well, I wanted to be visually appealing, and you see what I look like, so clearly we need pictures. And I've tried to be interesting for years, it never works. I said, this calls for a completely different approach, I need to start over. Do you find me more visually appealing now? And more interesting, too, right? All righty. I still want to talk about the last thing D needs. I'm going to be talking about C++, because this is a D conference. I'm not going to be casting C++ in the most complimentary light. Now, I could cast C++ in an extremely complimentary light if I chose to. I just want to say at the outset, lest people get the wrong impression, C++ is a very successful programming language. Its success speaks for itself. So according to the current information, the Black Duck Group says that it is the second most popular language for active open source projects right now. And for almost 25 years, it was either the second or the third most popular programming language according to the TiOB Programming Index. It's currently at number 4. A couple of months ago, Objective-C took it over. So there's lots of good things to say about C++, and most of them I'm not going to say today because I have a point I'm trying to make. And talking about how wonderful C++ is not that point. What I do want to emphasize is I'm not here to bash C++. That's not my goal. My goal is to come to a conclusion based on some observations that I want to make about C++. So don't misunderstand me into thinking, oh, Scott now thinks C++ is a horrible language. That's not what I'm talking about. It's important to have some information about someone's perspective when you're listening to them speak, because obviously that's going to color the opinions that they have. So you need to know a little bit about my job. I have actually a very unusual job from what I could tell. The first thing for this conference you need to know is my job's not D. My job is also not designing programming languages. I'm not a programming language designer. I'm going to make a confession which will make many of you instantly stop listening to me, which is I don't develop software. I used to develop software. It was a really long time ago. That's not my job anymore. Occasionally, my job is going to companies and consulting. Not very often. Much more frequently, I go to companies and I do training. People sit and they listen and I stand and I talk to them about C++, usually. There is a common thread that runs through what I do all the time, And that is, my job fundamentally is to explain things. I am a professional explainer. That's my job. Who knew that you could have a job doing that? Turns out you can actually make a career of it. But because my job is to be a professional explainer, the perspective that I tend to bring to things is things that are easy to explain, those are good. They make my life easy. Things that are hard to explain, I don't like those so much. And that's the perspective that I want to bring about right now. In case there is any ambiguity, all the code that I'm going to be showing in this talk is in C++. It might accidentally also be D, I don't know. But my assumption is we're compiling with a C++ compiler. I've always been envious of Andre's talks. Part of it is the sexy Eastern European accent, which I can't touch. But the other thing is, Andre has a really good way of engaging people. And at 9 o'clock in the morning, day 2 of the conference, it's kind of the sandwich day, we need to be engaged. So I'm going to do this in terms of a quiz. So all C++ code. I say int x1. What is the value of x1? 42. 42? Okay. Any other guesses? Okay. It's undetermined. Why? Okay. We're not initializing it? It's just, The standard says so? Okay. The answer is it depends. It is unknown, but it's only unknown because we don't have enough information. All right? So if we get a little more information, it's an unknown value, a little more information. So now I say int x2, this is at global scope. I still don't give it an initializer. Now what is its value? 0. Why 0? Because the standard says so. Why does the standard say so? There's a whole bunch of right answers to that question, by the way. Yeah? Okay, and why is that important? Okay, there are several answers I will accept. One of them is because that's what C does, which leads to the question, why does C do it? Which leads to Walter's answer, because it's done in the BSS section, which really boils down to because it has no runtime cost. Because it has no runtime cost, because we can do it for free. So and presumably the underlying thinking there is, undefined values are bad. Things should be initialized, but we don't want to pay for it. So if we can do it for free, we're going to give it to you. But if we can't do it for free, we're not going to. Presumably that's the underlying thinking there. I mean, there is a reason for everything. I mean, because they could have just said, it would have been just as easy, no, it would have been easier in the standard to say, uninitialized values are undefined. That would have been much easier from a standardization point of view. But they actually are more complicated than that. Alrighty, so that's 0. I say static int x3. What's its value? Also 0 for the same reason. It can be statically initialized. I say I've got a new int. It's on the heap. What is the value of this int on the heap? Okay, I hear 0, non-zero, and maybe 0. I will take the union of these answers as the group's official answer, and the answer is you are correct. The value is unknown. Why? And why does C++ not initialize heap memory? In other words, it has a runtime cost. Because we don't want to pay for things. We want nice, well-defined values as long as they're free. That's the underlying philosophy. It comes from C. Blame Kernighan and Ritchie. I open a scope. I declare int x4. What is the value of x4? Anything. Again, this would require runtime initialization, so the value is undefined or unspecified or whatever the official word is. Andre?
Repeat questions, please. Thank you.
Oh, okay. Sorry. So the value is unknown for the same reason, because it would incur a runtime cost to give it a value. All right, so I have an array. I have an array of 100 elements. What are the values? So the question is, where is the array? As if that matters. Oh, wait, it does. We don't know what the values in the array are because we don't know where the array is located. Okay, so I now have the same kind of an array, but now it's a global scope. Now what are the values? 0. Because we can initialize them conceptually before runtime, we don't have to pay any cost. Now, at this point, you look at the whole thing, you say, okay, what appears to be the rule here is that if we don't have to pay to initialize things at runtime, we get 0. If we do have to pay to initialize at runtime, we choose not to pay that cost and instead invest hundreds of programmer hours in debugging. That's the trade-off we've decided to make. If I have a static array, what are the values? 0, same thing. Great. I have a vector of int. Vector values are allocated on the heap, for those of you who have not been keeping track at home. What are the values of the ints in the vector? 0. That incurs a runtime cost. Now, my job is to explain to people what the initialization rules for integers are. It is not as easy as it might be. Okay, but that's just initialization. Let's move on to something even more fun. Let's do type deduction. Because there's just not enough type deduction going on in the world. I think we need more of that. All right, so I declare a constant int cx. A constant int cx. And now I say, I want to have a new variable, my cx1, which is initialized with cx, and the type will be determined by auto. Now, if you know the auto rules in C++, think of this as a quiz. If you don't know the auto rules in C++, guess as to what you think should happen. So the question is, what is the type of my cx1? Int. Why int?
I can't remember the rules, but I'm pretty sure that if you want a constant, you have to add const auto.
Okay, so the guess is it's int because he's pretty sure that if you remember the rules, you have to add const.
It's copied by value, so it's different.
Okay, exactly. So the comment is that this variable here, my cx1, is a completely new independent variable. So just because the thing that's initializing it is const doesn't mean this thing has to be const, which is correct. So the type is int. Sounds reasonable. All right, so another thing you can do in C++ is you can take the decal type of something. So I say decal type of cx. This is going to give me the type of cx, my cx2. Now, what is the type of my cx2? Sorry? Constant. Why constant? Because that's what the standard says. And it turns out, yes, it's constant in this case. It actually preserves the constness in that case. So a different kind of type deduction. You know, I don't think we've seen enough templates. I'm on slide 8. We haven't seen any templates yet. That's sad. So I have a template, f1. It takes a type parameter t by value. I call f1 with this const int. T has to be deduced. What is t? Int. You say, anybody think other than int? Okay, guess for constant. Why int?
This is because, if I remember correctly, the rules for auto is the same as for templates. Because there's a new decal type thing.
You know, see, he goes, if I remember correctly, the rules for auto were the same as the rules for templates. That's so cute. I'm sorry, excuse me. In case I was not clear, this is a talk about C++. Still not here to bash, really. All right, so the thing is, param is going to be a copy of cx. And because it's a copy, it's a completely independent chunk of memory. Just because this is const doesn't mean this should be const. Same reasoning as for auto. Different rules, but same reasoning. So it turns out that in this case, the type is int. All right, so another template. It now takes a reference to t. I now pass in cx. What is t? Constant. Why? Because we are referring to a chunk of memory, and since we're referring to a chunk of memory, if it's const, we want to make sure that what we're referring to, we preserve the constness of it. True. So it's constant. I now have another template, because I can, and it takes an R value reference to t, although what I've argued should be known as a universal reference to t. I pass in cx. What is the type that is deduced for t? I hear constant, I hear const t ref, which I'm going to assume really means const int ref. Okay, why constant ref? No, so the answer is correct. It actually is const int ref. Why constant ref?
Because it's an L value, CX is.
Okay, yeah. What I'm looking for is not what is the rule, but why is the rule that way. There's a reason for everything.
Because if you pass by reference, you get a constant const. Otherwise, you can mute it something const.
Well, that explains why we preserve the const. The question is, why is the reference being added? Because notice there's already a reference here. Okay, that actually is the answer. He says it's a neat trick to allow argument forwarding. Why does it behave this way? It behaves this way because this is what they needed to do in order to achieve some other end, which actually was known as perfect forwarding. It's a hack. I'm sorry, it is a special rule. They said, we have a problem we want to solve. And this allows us to solve that problem. It's a special rule for solving a particular problem. Fair enough. All right, so lambda expressions. I have a const int cx. I now this creates a lambda. This says, I'm going to capture the local variable cx. Now, this expression here will cause the compiler to generate a class, which I've called class up to the compiler. It generates a class with some compiler-generated name. It will then take this local variable cx, which is mentioned here, and it will then create a data member with effectively the same name inside the class. So practically speaking, what we're doing is we're copying this variable in the local environment into the data member of this class. That's what's going on. So this is going to copy the value of cx into this data member, also called cx. The type of this variable here is const int. What is the type of the data member? Int. Why int?
Copy by value, same reason.
Copy by value, same reason. Okay? I'm sorry, you're wrong. It's const int. Did I mention this is a talk on C++? Okay. It's constant, and because it's constant, this also means this code won't compile. We are attempting here to make an assignment to a const. So this is with lambdas. This, by the way, is, as far as I know, the only context in C++ where if something is const and you make a completely independent copy, it preserves the constness. Why? Everything's there for a reason. As far as I know, no one on the standardization committee says, this is really going to mess Scott up. Let's do it this way. Lambdas are funny things. Yeah, go ahead.
I think it's because if you have if you capture all the context, then you could inadvertently assign variable as opposed to specifically naming the X.
Okay, I'm not sure. It's possible you're saying what I'm going to say. I'm just not certain. So, lambdas are funny because with lambdas you're dealing with two scopes simultaneously. Inside these curly braces here, you're actually inside the scope of this class. So this CX actually refers to this chunk of data here. But visually, if you're looking at the source code, this CX looks like this CX, visually. And it's a funny kind of thing to intellectually shift from, oh, this CX is in the outer scope and this CX is in a class I can't see. So I believe the reasoning is, because this is const here, and you're going to think you're manipulating it here, but you're not. If this thing in the outer scope has been declared const, we're going to copy a const down here so you don't accidentally modify a chunk of memory other than the one you think you are. I believe that was the reasoning behind this. Makes some sense to me. They're trying to prevent user errors. You're programming in two scopes at once now. It's a funny thing to do. So in C++ 14, the most recent version of C++, they added something known as a init capture. So here's an init capture. So what this says is, I want to declare a local data member called CX, that's this CX, whose initial value is this CX, that's this CX. I feel silly explaining this, it's so obvious. So this says the local variable CX is initialized with this CX. So what's the type of CX? You give up, we're on slide 10. Okay, now, it turns out that it is int, that's correct, but it acts like constant. This won't compile because we're attempting to make an assignment to this CX. Why? Sorry? Someone said over here? No, this is actually a totally different reason. This is a totally different reason. No, the reason now is because the function call operator inside this class is declared const, and because it's declared const, this int, which is not const, becomes const inside the class. How have you people been wasting your lives not to know this? All right, but it's easy to fix. It's easy to fix, no problem. What we do... It's easy to fix. We slap a mutable on the lambda. Now, by slapping a mutable on the lambda, that causes the const, which was added to the function call operator, to be removed. Okay? Except this won't compile. Why? It's perfect. It's not valid syntax. Why? Because you have to put the parentheses here. Why? Because they failed to include the grammar production to omit empty parentheses in mutable lambdas. Still not here to bash. Alrighty. So now we got the mutable lambda here. What is the type of CX here? From the man who teaches comparative programming languages. Alrighty, type is int, and now it actually acts like it, which is kind of cool. So here's the situation. By the way, notice I'm dealing with int. I didn't have to use any fancy user-defined types to play these games. So const int cx actually can be deduced in 7 different ways and gets not 7 answers, but there's 7 different contexts, except I lied. There's only 6 contexts because it turns out that auto and lambda init capture are the same, but auto and template are almost the same, but not quite the same. So that's type deduction in C++ 14. Those of you who are young and have a long career in front of you, you could spend the next 10 years studying this stuff. Wouldn't that be fun? Okay, more type deduction. 4 ways, there's no type deduction yet. 4 ways to declare an integer and give it the value 0. All 4 of these syntaxes, with the equal sign, with the parentheses, with the equals and the braces, or just with the braces, initializes an int to 0. They all do the same thing. Really, I promise. For an int. We're not going to get any more complicated than ints. We don't need to get more complicated than ints. Okay, auto x1 is 0. What is the type of x1? Obviously int, right? It is int. No trick questions. Auto x2, 0. What is the type of x2? Int. No trick questions. Yet. Auto x3, brace 0, brace. What is the type of x3? Initializer list of int, of course. And what is the type of this one?
I got that one right. I'm looking at
The guy's like, I got one right, I'm quitting, so. Yeah, he quit on slide 10. Come on. All right. Also initializer list of int. Now, but you might think, well, that's all right, because maybe it has been defined that the type of brace 0 brace, maybe that type is initializer list. And auto is just deducing the appropriate type. Now, we might have a little trouble because we'd wonder what's going on up here, but set that aside. So let's test that. So here's a template. And what I do is I've got a by-value parameter. Here's t. I pass in f of brace 0 brace. What happens?
array.
What's that?
An array.
An array event, no, good guess, but not correct. Initializer list, excellent guess, but would be too obvious, no. It doesn't compile because brace 0 brace has no type. You might wonder, well, okay, what's going on here? Who made the cute comment about auto and template type deduction being this? It's so cute. Special rule for auto. Why? I have tried for years to find out why there is a special rule for auto and initializer list type deduction. There's got to be a reason. The standardization committee voted in. I have never been able to find out what the reason is. The standard is very complicated, but it doesn't change the fact that somebody came up with these semantics and said there's got to be a reason for them. I just don't know what they're. Okay, enough of this. Okay. Too many angle brackets. Inheritance. You can't get this wrong. Really? You can't get this wrong. Base class has a function do base work. Derived class inherits from the base class. It makes a call to do base work. Will this compile? Yes or no? This is not a trick question. Yes, this will compile. This is normal run-of-the-mill inheritance. No surprises. So let's generalize things because we can. All I'm doing is templatizing the base and the derived class. That's all I've done. Will this compile? Actually, I need to say, should this compile, as there seems to be some disagreement on the part of major compiler vendors. Should this compile? No. Why not? Pardon me? Okay, it's a dependent base class, and why is that important? Okay, so we've got two-phase lookup. Why? Why do we have two-phase lookup?
Because of specializations.
Okay, and in particular, what about a specialization?
Well, if it's looked up early, because specializations are defined afterwards.
Okay, so essentially, it's the problem is there could be a later specialization of the base class, which the compiler has not seen yet, which for base of int, it doesn't actually have the do base work function.
I got one right.
You did get one right. I mean, you teach it for a living, so only half credit. If you want to post to your Facebook page, I got a C++ question right at a D conference, that's fine.
I'm going to post because I'm not doing C++ anymore. Scott talked me out of it.
Only the strong survive. Alrighty. So this doesn't compile because there could be a later specialization. All right, but let's suppose as the author you go, there are no freaking later specializations. Darn it, I wanted to compile, so what do?
Base T, qualify it.
You can do base T : that will work. It also has the disadvantage, which is not relevant here, but in general it turns off virtual function calls, which is, pardon me? This arrow, exactly. There's three ways to do it, but this is one, is to say this arrow. Now this will look it up in phase 1 instead of phase 2. I think everybody in this room knows that who is facing this direction, from what I can tell. Okay, computational complexity. I have a vector. I sort the vector from begin to end. This first question, does this compile? Yes, correct. It does compile. Why does it compile? It compiles because sort requires random access iterators in order to do its work, and vector offers random access iterators. And what is the computational complexity of this call, of sorting a vector? N log n. Excellent. That's true. It's true. The standard says officially it's O of n squared. But every library that I know of does it in O of n log n. But officially it's n squared. All right, so now I have a list. It's a linked list. It's a doubly linked list for what it's worth. I call sort on the list. Compile or not compile? How many people think it does compile? Excellent. You're all right. It does not compile. Why does it not compile? Because list doesn't have random access iterators. Exactly. So this is an error. This will not compile. I do a binary search from the beginning of the vector to the end of the vector for the number 10. Doing a binary search, I'm going to assume now the vector's sorted. It's a precondition for calling binary search. Does this compile? Yep. And what is the complexity? Binary search, log n, right? Cool. I do a binary search on the doubly linked list. Does this compile? Does this compile? How many think it compiles? There's a few suspicious people. Okay, you are correct. It does compile. The complexity is O of n. What is the official complexity? That's not what the standard says. The standard doesn't say O of n. It's linear. It's a linked list. Pardon me?
I think the official complexity is n log n.
The official complexity for binary search is log n. The official complexity is log n. Anybody happen to know how they pull that off?
You can have increasing steps into linked lists. You can have it, but I don't think list has that.
It's all done with iterators. So the comment is if you had special iterators that move forward. The problem is you have to follow all those links. No matter what kind of an iterator, you still have to follow all those links. It's a doubly linked list. So it is, in fact, linear. The official complexity is log n. Anybody know how they pulled that off? Exactly, exactly. The official complexity is based on the number of comparisons that are performed, even though the number of comparisons is going to be swamped in normal operation by the number of iterator steps to actually get to the point where you can do the comparison. Okay. Alrighty. By the way, as I said, I can give a much longer talk on how wonderful C++ is, but I'm going somewhere with this. There's a bunch of containers where if you want to get rid of all the values equal to something, you can call a member function. So for example, if I have a set of int, if I want to get rid of all the copies of 14 in the set, I call erase. So the member function is named erase. So the member function to call for set is erase. That's the member function that you call. So let's suppose I don't have a set, I have a multiset. What's the member function you call to get rid of all the elements equal to a particular value in a multiset? Oh, guess. Erase. Perfect. Excellent guess. What about map? Erase. Excellent. What about multimap?
Erase.
Erase. Okay, what about the unordered equivalents, the hash table versions? We'll do all 4 of them at once. They all use the same member function. What's it called?
Erase.
Excellent. Erase, 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 erase. There's a trend here. For a list, I want to get rid of all the elements with a particular value. What do I call?
Erase.
Remove. Exactly. Erase, that's crazy talk. Forward list.
Take out.
Take out. We don't go around inventing new names. That's silly. It's also remove. Alrighty. If you have a sorting algorithm, it can be stable or unstable. It doesn't even matter what that means. Most of you probably know, but it's immaterial. It can either be stable or not stable. So I have a sort algorithm. Is it guaranteed to be stable? Not guaranteed to be stable. You're correct. I have an algorithm called stable sort. Is it guaranteed to be stable? No. What kind of twisted language would have that on it? Clearly, it's guaranteed to be stable. All right, maybe not so clear. There is a member function in the list class called sort. Is it guaranteed to be stable? Oh, you got a 50-50 shot. Is it guaranteed to be stable?
Yes.
How many say it is guaranteed to be stable? How many say it is not guaranteed to be stable? All right, so it's a 50-50 shot, right? Okay. It's guaranteed to be stable. And At one point, I tried to convince members of the standardization committee that this made no sense, that if you have a sort that's guaranteed to be stable, it should be called stable sort. And they said, well, there's no reason to name it stable sort. It's defined to be stable. And it reminded me of a movie. It's like, well, it goes to 11. I mean, why make 10 louder? It goes to 11. Okay. Last example, FOMA specifications. So there are what are known as sequence containers in C++. So these are the 16 requirements to be a sequence container. They're the requirements for a sequence container. I've copied this out of the standard. Sequence container requirements. There are 5 sequence containers. Here are the 5. Very simple question. Which of these 5 satisfy the requirements to be a sequence container? Okay, so array, yes or no? So the question is, can we go back and look at the requirements real quick? Sure. That should give you plenty of time. The answer is no. Array does not satisfy the requirements. I mean, it'd be silly. Why would you have a sequence container satisfy the requirements for a sequence container? What about dec? Dec, yes. What about forward list? Forward list, the answer is not no. It is hell no. It satisfies 1 of 16. That's 6.25% of the requirements, which apparently is a passing grade. What about list? List, yes. Vector, yes. Fred Brooks wrote an article a number of years ago in the 1980s called No Silver Bullet, and he introduced these terms of essential and accidental complexity. He wasn't talking about programming language design. He was talking about building software systems. But I'm going to sort of take over these terms and use them in the context of programming language design. Essential complexity, in my view, is there's just something complicated and hard in the world, and you have to deal with it somehow. And it might come about from competing design tensions. So for example, you want to have a really, really expressive language. Let people do whatever they want. It's a complicated world. People need to write complicated programs. But at the same time, you'd like the language to be simple and regular. And it's not always easy to make those two things go together. You want to have high levels of abstraction. You want to have portability across architectures, but you want it to be maximally efficient. It's not always easy to balance those things. After your language has been around for a while, there's legacy code. You want to not break legacy code. People don't really like having their programs get broken. But at the same time, new information, new ways of doing things, you'd like to introduce new ideas. Not easy to balance those things. You'd like to have a really expressive language, let the human do whatever they want. The compiler's not going to always really understand the goal, but you'd like to offer really good diagnostics at the same time in case something goes wrong. Not easy to balance these things. And I want to give an example. So I have a struct point, has 2 variables, x and y. Now, point : x, that's this variable right here. What is its type? This is not a trick question. It's int. I think we can all agree it's int. If I have a point P, and then CP is a reference to this point, but is a reference to a constant version of it, it's a const access path. What is the type of CP.x? Now, on the one hand, you could say, well, CP is actually referring to a point and x's type is int. We just agreed. So the type is int. But you could also argue, wait a minute, through this particular access path, the type is const int. And they're actually both legitimate ways of looking at it. So C++ actually gives you 2 ways to do it. Now, you might argue with the syntax. CP.x is int, and if you throw extra parentheses, it's const int ref. Again, you might not like the way that they solve the problem, but it doesn't change the fact that there is a fundamental ambiguity in the question. If I have a similar example to what I showed with the template inheritance, in this case I've got do base work, but notice that I've omitted the O. So this is to base work. So it doesn't match this here. Now, you sort of have a couple of choices from a language design point of view. What you could say is, I'm going to assume this is a typo and issue a diagnostic now. But if you do, you can't specialize it later. Or you could say, okay, what I'm going to do is I'm going to assume that there will be a later specialization, and I'm not going to issue a diagnostic until somebody actually instantiates it. The problem there is if it really is a typo, if the library author just made a mistake, the error message will be given to the person using the library rather than the library author, and that doesn't seem right either. So the C++ solution is to give the author of the template control. Basically, do base work says do an early lookup. This arrow do base work says do a later lookup. Now there's other ways to solve this problem, but once you've introduced the idea of templates and specializations, the problem exists. You've got to solve it somehow. These are examples of what I consider essential complexity. It's not an arbitrary, wacky decision. There are some arbitrary, wacky decisions, in my opinion. Things like ints are sometimes initialized to 0. Things like by-value lambda capture sometimes retains the constness. These are all examples of things we saw earlier. There's a lot of, in my opinion, simple arbitrary choices that did not have to be made that make explaining things more complicated and also make working with the tool more complicated. C++ at this point, it's been around for over 25 years, it is too complicated to fix. And it has too many legacy constraints on what's going on to realistically make any real changes. What's interesting is, during the first round of standardization, which took place in 1990 up to 1997, one of the things you heard really frequently during the standardization process was most C++ code is yet to be written. The idea was, look, there's some stuff we've done in the past, but forward is where we want to face. I have not heard that phrase in years. I don't think C++ thinks of itself that way any longer. At this point, there's billions of lines of C++. You're not going to go around breaking that without a good reason. Perhaps more importantly, it is my perception that there is no real interest on the part of the C++ user community or the standardization committee in dealing with these kinds of issues. I don't think they think it's a problem. And I think that if you talked to every individual member of the standardization committee and you said, are you concerned about inconsistency and arbitrary decisions and simplicity and ease of explanation, they would all say, yes, those are very important. And they would not be lying. Every member of the committee would say, yes, those are really important to me. But in my opinion, if you look at the results of their work, the resulting standardization document, the decisions they ultimately made as a committee, they do not reflect that concern. There is epicycle on epicycle on epicycle inside this language. I think there's a lot of really well-meaning people. They do have it as a priority. The problem is it's priority number 22 over some other ones. D is a younger language. It is a younger library. It's got a smaller user community. It's got a legacy code, a much smaller legacy code base. There is still time, if it hasn't already been done, with any luck, this isn't even an issue in the D community, but there's still time to embrace a holistic, easy to explain is good philosophy. When I talk about holistic, I want to contrast that with piecemeal. In C++, for almost any rule in C++, if somebody were to say to me, why does that exist? I can probably tell you. And I can probably give you a rational explanation for why it's there. Everything's there for a reason, except the auto type deduction rule. Everything is there for a reason. But a holistic approach says each language rule is easy to justify in isolation as well as in the context of the other rules. That's what C++ does not have. What C++ has instead is a whole series of justifications that they trot out on demand. So here are some of the more popular things you'll hear to justify things in C++. It's got to be compatible with C. We need to maximize efficiency. You don't pay for what you don't use. Trust the user. Prevent likely errors. General features. Don't constrain compilers. Favor users over compiler writers. Be backward compatible. Be consistent. All legitimate sounding things. But what I find interesting is you can justify anything with those two. And you can justify anything with those two. And so what tends to happen during C++ standardization is they trot out whichever justification makes sense for the rule that they want to adopt. And they now have enough rules that it doesn't matter because they can justify anything. The comment is it's like the tax code. And it's actually sort of interesting that you mentioned that because the only thing that I know of that I have personally have some experience with that is more complicated than C++ is the US tax code. But in fairness, it's had a couple of hundred years to be built up, so it's not quite a fair comparison. I want to talk a little bit about tool use versus tool application. So we've got a table saw and we've got a sander, things for working with wood. Table saws cut wood, sanders make it smooth. That's using a tool. These are some gardening tools. So you stick them in the ground, you move dirt around, or you cultivate plants, whatever it is you happen to do. Garden tools. These are dental tools. They're used for torturing people. When you learn the basics of using tools, how to move dirt around, how to scrape plaque from between teeth, how to cut a piece of wood, that's what I call tool use. Tool application is some higher level aspiration of what you're trying to achieve by using the tools. So the table saw and the sander, maybe what you want to build is a really nice bookcase. With the garden tools, maybe what you want to do is a really nice formal garden. With the dental tools, you want to have somebody have a smile that looks like they're in an advertisement. Those are the higher level aspirations that you want to have. So with the table saw, tool use. It's dealing with things like, okay, how do you attach and remove the blade? How do you raise and lower the blade or give it an angle? Sort of how to use the tool fundamentally. How basic safety precautions, so you don't cut off a finger or you could poke an eye out with that thing. In C++, the equivalent level of talking about tool use is things like, what are the rules governing the compiler-generated special functions? How does type deduction work? All 6 forms of it, I might add. How does reference collapsing work? What about dependent and independent names? These are really low-level, language-level things. Tool application, when you're trying to aspire to something greater, it's more than just the basic use of the tool. For a table saw, it includes things like, okay, cutting the wood is one thing, but how do you cut the wood so it doesn't splinter along the cut edge so it's suitable for furniture when you're finished? That requires some technique that you're probably not going to find in the manual. Or table saws are great for cutting things at 90-degree angles. That's what they're kind of designed for, 90 and 180-degree angles. But what if you need a 22.5-degree angle? How do you cut a tapered leg? That calls for a little more finesse, a little more knowledge. If you're going to be putting nails in the wood and you're going to sink the nail holes, so now you've got holes that need to be filled, but you want to make sure that it's filled with exactly the color wood that you just cut, you can mix the sawdust with some putty and put it in there, and because it's got the same wood, it'll match it exactly. That's application of a table saw. In C++, applications that I've dealt with, working with some real clients, things like how do you replace virtual functions with templates in a physics simulator? I did some consulting a number of years ago at Lawrence Livermore National Labs. If you ever get a chance to work at Lawrence Livermore Labs as a consultant, I encourage you to do it. Really smart people, really interesting people. One of the things they do there is they design nuclear bombs. And one day they said to me, Scott, if we don't do our job right, millions of people could live. Sort of puts it in perspective, doesn't it? How to use template metaprogramming to generate code for dispatch tables in an embedded automotive system. Went and worked with a group of people, that's what they needed to be able to do, and they had a whole bunch of really icky code, which they didn't want to maintain, which was compressed into a much smaller amount of, to the uninitiated, much ickier looking template code, but it was much more maintainable, did exactly what they wanted to be able to do. That's an application. Things like how to use Lambdas to initialize const data structures, or how to use nth element and sort together to get better performance than partial sort. That's tool application. That's the more interesting stuff, in my opinion. So sad. So the last quarter century of my life, I have done a couple of other things. Raised the dog. So this book, 55 guidelines for C++, this one 35, this one 50. I'm working on a new book now. It's going to have 42 guidelines because a friend of mine keeps nagging me to use 42 as an arbitrary number. If you add these things together, I've got 182 guidelines. Now, 182 guidelines, That's an awful lot of stuff to remember about a programming language. That's on top of all the stuff you have to remember for the APIs that you're using that are not part of the standard library. Not to mention, you're trying to get some work done to do something. Some of what I've written about has been tool application. But much too much of what I've written about has been tool use. Talking about language idiosyncrasies, arbitrary decisions, things you need to be able to remember. So the message that I bring to the D community, based on my experience with C++, is that the last thing D needs is somebody like me. Any questions? Yes? When will the new book be out? The new book should be out probably, I would guess, late September, early October. I have an absolute drop-dead delivery date of September 5th. So that's when the final manuscript will go to the publisher.
In fact, someone on the stream asked when we're going to see effective D.
I don't know. You're not supposed to need it. Yeah. So. In fairness, there could be an effective D that would talk about how to apply the features of D in an effective manner. As I said, I've written about tool application to some degree, and I think it makes a lot of sense to have a book that talks about interesting ways to apply the features of D to achieve higher level ends. That, I think, would make a good book for any programming language. I would just hope that such a book would be focusing on the application level stuff as opposed to the lower level use kind of stuff. Any other questions? Yeah.
You say you're not a language designer and you haven't designed a language. Well, how can you resist the urge?
I guess I went through that phase of my life when I was in graduate school when everybody was designing languages. And at this point, I just realized it's a hard problem. It's not easy to do, and it calls for different skills than what I do. So I think what I do is legitimate and helpful to some people, and I think language design is a legitimate skill and helpful to people as well. So it's just not the same thing.
We had another question on the live stream, which was, is it your view that it's better to make a breaking change now than to leave a broken or confusing design in place? Of course, I'm guessing there's no binary answer, but what would you consider would be your kind of heuristic for figuring out whether to leave something broken or not?
Anytime you're thinking about a breaking change, you're trying to evaluate how big is the problem we're trying. How many people are going to be broken? How serious is it going to be? Is it a silent break or a non-silent break? You take all of those kinds into account. I think that when a user community is comparatively small, when a technology is comparatively young, it makes more sense to break things more frequently because you're still in the learning phase. I think that as you get a more mature technology and as you have more and more people who are dependent on the stability of that technology, you have to be a little bit more conservative. So other than that, that's sort of my general answer.
I think we had one more here, which actually was very specific to C++. So with the addition of recent standards and the addition of working groups, which I think is setting this up for being a rhetorical question, has the pace of change in C++ quickened?
Oh, the pace of change in C++ is dramatically faster. Nothing changed for 13 years. And now they have consciously adopted a standardization schedule where basically things will be changing fairly significantly, probably every 3 years, which is going to have some really interesting implications. One of them will be that it is going to be more difficult to find up-to-date, accurate information because if things are changing every 2 or 3 years, you might find, for example, an answer on Stack Overflow or in a news group or a blog article or whatever, which was perfectly accurate when it was written. But if it's more than 2 or 3 years old, it could now be out of date. So it's going to introduce a whole series of new problems in C++ programming. At the same time, it's going to give a whole lot of new tools to C++ programmers they've never had before. So it's an exciting time, but it's going to be more complicated, which really is what we needed.
Okay, so we have, I think, a great opportunity for another round of applause for Scott. Thank you very much.
Thank you very much.
And we'll start again promptly in 5 minutes with Maxime.